this stuff in class up through this week. Okay, you can bring any notes you want, printed out notes you want from class, but you can't use any sort of electronic devices. So there should not need to be any calculations other than like adding that you'll need to do. So you shouldn't need calculators or anything like that. So I'll talk more about that later on, but just to give you a sense of how to start preparing for that. And then the intermediate report is the next step due for the project, which is going to be due the Monday after spring break. And also on that day, we're going to do some peer review in class as well. So I'm going to have you paired up with a couple of other groups that hopefully are doing projects in a somewhat similar space if they can, and you guys are going to talk with each other, and you're going to see each other's reports, your intermediate reports. If you have some data that is sensitive for whatever reason, and you can't share certain aspects with them, but you can with me, let me know ahead of time, and we'll figure something out. Okay, question.
What number day is that?
It's Monday, March 21st. Is that, so I'll expect everyone in class for that if possible. If you can't be in class for that, let me know ahead of time. Okay, so we're starting, so that's kind of the administrative business. We're now starting a new kind of small section of class on streaming algorithms. So that's going to be covered this week, but then we're going to revisit some of these issues in the regression part of the class and maybe in the graph analysis part of the class as well. Okay, so who's heard of a streaming algorithm before? Who's heard of this term? Okay, so a few of you have heard of this. Right, so the main idea here is that you have some so you have some large data, but you don't have access to it as you normally would. It's not sitting on the disk of your computer, or maybe it's sitting on the disk, but it's definitely not just sitting in the memory of your computer. In fact, the data could be arriving more data all the time. So what's going to happen is that you're going to be you could think of this data actually as some long string, and each data element is in this long list or this array. Each data element is in this array, and up to time I, let's say, up to time I, you have access to data points. Say, let's call this A1, A2, A3, up to AI. You have access to this part of the data only. Okay? So there's other data that you're going to get access to, but you have to process the data you've seen so far. And the constraint is that as you're processing it, you're often sitting down here, and so sometimes you draw a picture of something that looks like a CPU, but really you think of this CPU plus some small memory on the side, and the memory is small compared to the data. So you can't store all of the data. You can store some part of what you've seen, but you can't possibly store everything. Okay? And so you need to process this data up to this time I, and you need to fit whatever you're processing inside of this part of the memory. And then you're going to get another data point, and you have to process that, and you have to deal with it. And you have a limited amount of space you have to deal with here. Okay? So kind of where this was first, at least as I understand and from the algorithms community, where this was first really kind of investigated heavily and found applications was where this object here is like a router, and the data are all the packets going through the router. Okay, so the router can't store all the packets going through. It's not a storage thing, it's a router. It just sees them, it does something with them very quickly, and then it moves on to the next one. It can't possibly store everything. So if you want to keep some basic statistics of what's happened on your data, you have to do it in this model where you have a limited memory that you've allocated, maybe not even the full memory of the router. You have some memory on the side that you want to kind of use for keeping track of what's going on with all these packets, right? So this is one application. Another one is where this data that you have, this big data set, lives on disk, or it lives somewhere else on the network. It lives in the cloud, and you want to, and it doesn't all fit in your memory. So one efficient way to deal with this data is to read through it once. You get one chance to read the data. You don't have random access anymore. Okay, so a traditional model, if you're looking at a basic class in algorithms, is you assume that you can go and access any piece of the data at any point and maybe do a modification or a comparison. And this takes a constant amount of time. When your data is really big, this is no longer true. Okay, so one way of dealing with this, and this is not the only way, is to say, I'm going to only deal with the algorithms that make one pass or maybe a few passes over the data. Okay, I'm just going to read it once, you bring it into memory, you read through it, and then you replace that with something else from memory. You have these blocks in your memory. Okay, and so maybe you can keep a few blocks in your memory, but you might want to have other stuff running and so forth. So you want to keep the data in your local memory much smaller compared to the full data set size. Okay? It turns out that the sorts of things you're going to want to keep in the memory are going to be useful for even broader sorts of applications where you're doing things in parallel and you want to kind of summarize the data and send these summaries back and forth. But we won't get into this so much now. Maybe a little bit into the regression part of class, where we'll see some more advanced sort of these techniques. Okay, so does everyone roughly understand the model? We'll go through several examples. Okay, so let's talk a little bit more about what these data can look like, and we'll stick with this router analogy. It's often good to think of, and you need to be careful often in thinking, what does this data actually need? Because you need to be careful with the memory in this case, right? So we're going to think of each of these data elements as coming from some universe n. Okay, so again, I'm using this notation where it's from some set of size n, and I can use the numbers 1 through n to represent it. This could be all IP addresses. This could be all words in the English language and so forth. There's some universe. There's some universe of the data that it comes from. And the important thing is that I need to be able to distinguish between two different things in this universe. So this is going to take so the space of one, this is too small, of one AI is going to be roughly log of n. Okay? So I'm going to need this many bits in order to represent something in a universe of size n. Okay, so maybe, if I do various encoding schemes that maybe are more efficient, maybe I'm off by some constants or something, but roughly you want to think of logarithmic in n, the size of this, domain. Now often we'll think of this log n as fitting in, say, one word of data, but we'll kind of, so say it's you can usually map something to an integer or to a float or something like this, and this will often be sufficient if you're using some hashing techniques to store these things. And you maybe don't worry about these collisions, but you want to know roughly how big this is, and log n is the right thing to think about here. Okay? The other thing that we want to worry about, and I'll get into some examples of this universe in a second. The other thing to think about is that we're going to have our data set A go from A1, A2, up to AM. So this M parameter here, the size of the data set, and we may not need to know this in advance, we need to know roughly how big this data set is going to get. This tells us how many, if we're going to keep a counter of something, how many items we've seen, that we need something that is in, so then a counter is going to take log of M space. Okay, so we're going to be able to do things like keep counters. How many things have we seen? That takes log M space. And each individual thing that we want to keep track of takes log n space. These should both be drastically less than n, the space of all IP addresses, which we don't want to deal with, or the space of all of our data set, which is going to be too big to fit in memory. But a log n and a log m are things we can deal with, right? So these are things like a single word. Okay. Okay. So in our, so what could be, so this universe of data, you know, again, we can think of IP addresses, but what can we possibly do with this? A common goal is to keep track of the frequencies of various items. How many times have we seen something from a specific IP address or going to a specific IP address? Say there's a certain word we want to keep track of. Maybe it has to do with its flag for terrorism. We want to keep track of that specific word. How many times did that word appear in this long string of text that we're seeing over these documents we're not secretly monitoring, right? So we'll index. So we'll index into this. We'll say for an index j in this domain n, we'll say that fj is the frequency. Okay, it's the frequency, and this is going to be, let's write this in the set notation. So for all AI in our data set, so for all AI in the data set, such that AI is equal to j. Okay, so this is the set of all things we've seen in the stream that is this j item. It's the specific IP address which is sending out all this spam or something. We want to keep track of. If it happens too much, it's probably something bad is going on there. So we care about the size of this. So then this tells me the size of this set. Okay, so this is the frequency. Okay, and so a common thing is we want to maintain the frequencies of all these items to see if any one of them is getting too big. If something is getting too big, that's interesting. Okay, Another view of this is that you can kind of, if you normalize this, so if you do f of j divided by m, which is the number of things that we've seen so far, or the number of items in the data set, this kind of gives us the probability of seeing item j. This is the probability of seeing j. Right, of seeing this j thing, or at least our empirical probability, okay? And what's interesting, if we've seen something once, this might just be noise. We can maybe, unless we knew ahead of time this was something specific we wanted to look for with some filter, otherwise we would just say that the things that occur infrequently are probably noise. We care about the things that have large values. And it turns out only the things with really large values are the things we're going to be able to detect in small space. Okay? So we're not going to be able to really find things that occur infrequently, but things that occur very frequently we should be able to pick up only using a small amount of space. Okay. Okay. So this is the problem, or I guess this is the setup. There's some. Let me mention a couple of generalizations of frequencies that kind of fit. There are two generalizations, and then we'll talk about some algorithms, and we'll hit on one of these generalizations today and another one of them in a few weeks. So in addition to the frequencies, it's sometimes useful to look at what's known as the quantiles, and this requires so this requires an ordering. It's specifically an ordering on n, on this universe. Okay, so instead of thinking about this now as the IP address of a packet, which is a discrete object, two different IP addresses, even if they're right next to each other, maybe that probably does mean something, but it doesn't necessarily say one is better or less than the other. You could think about this as something like the time it takes a packet to reach from here from here from the previous router, something more continuous, right? Or you can be looking at this data, and this is the amount of money a customer spent on a website, or the amount of time they spent on it before they clicked on a link, right? The amount of time they browsed before they actually bought something. These websites are actually trying to measure these quantities, and they see lots and lots of customers, so they don't keep track of all this data. They want to maintain this statistics on this on the server. So you have an ordering on this, and then if two items are close, if two times are close to each other, that's useful to know. Okay, so instead, what we want to do is think of these the space n, kind of this is like equals to time, or it could be something else like money, some continuous value, and then you have these instances which you see on here, which have different time values, right? So people spent a different amount of time on the website. Okay, and now it's useful not just keeping track of these. Now these may not ever be exactly the same. You probably have some finite resolution, so they probably will be the same sometimes. But you don't have to think of them as being exactly the same. Instead, you can think of this as a cumulative density function here. So you get some thing that looks like this, where it goes from 0 to 1, and this is, the height of this is the probability that I've seen that the next item, or the item that I've seen, took this much time or less. Okay, so you can think of this as a cumulative density function. You did this for your homeworks, and so far you built these. So now we can think of this as the underlying object instead of just these individual counts. And then you think of approximating this cumulative density function, and you want to approximate it with something else. It turns out it's going to be also discrete, but ahead of time, just for the purposes of this, you won't care, such that the difference in the height, the difference in the error between this at all times is bounded. So this will be some bounded error epsilon. So say it's like 1%. Right? So you might want to approximate this sort of quantity. Okay, so this is a different generalization where you have an ordering, and we'll talk about a very simple way to do this towards the end of the lecture. And then the second generalization is that in the first one we just had a set of items. So this is where we're going to view the data as a matrix, and now this elements in n, this is going to be replaced by a point in RD. Okay, so it's a d-dimensional vector. So now you have more than ordering. You don't really have an ordering between them anymore because we have a higher dimensional value. But you want to think of kind of like, you can think of this as being these higher dimensional points representing more complex objects. Okay, and so then you're going to need to use different techniques. It turns out that the techniques we'll talk about today are going to generalize towards dealing with these points in higher dimensions, but has to use some machinery from SVD and PCA first. So we'll discuss that in a couple weeks, and then we'll revisit these to talk about how to do it in a stream in large-scale settings. Okay. So these are some of the kind of the classic problems in the setting that study, and these are kind of used as building blocks for lots of other things. You can get your data into one of these formats. These are things you can actually approximate. Okay, so let's go into talking about just the frequencies now and see how this works. Any questions before I move on? Okay, so the first thing we're going to talk about is a really simple problem called called the majority problem. And this basically is if some fj has a count greater than m over 2, I want to output j, else I can output, I can do anything, okay? So I want to know if there's a counter that has more than half. This should be, just has more than half, strictly more than half of the data, okay? So, with all the elections happening now, you only care about if someone has more than half the votes. If there's a tie or someone has less than half the votes, I can output something arbitrary, apparently. Okay, so this is one view of it. Another thing is, this threshold n over 2, we'll be able to relax that in a little bit, but think of this as you're monitoring traffic on a router, and say you only care about telling some specific IP address that they have a problem if more than half of the data coming through is from their IP address. If it's less than half or equal to half, you say, well, that's bad, but at that point I don't really care. And maybe this is over a short period of time or something like that. Okay, so it's kind of a toy problem. We'll use this to build up to do more cooler stuff. But you understand the problem. You only care if something's greater than half. Okay, so this problem should be easy. It seems like it should be very easy to do. But we're going to do it with only one label and one counter. Okay, if you remember, this label took log n space, and this counter took log m space, right? So a counter is because if there are m items possibly in the data set, you need log m space for counter, roughly that much, and log n if there are n items in the universe. So I'm going to be able to solve this specific problem using only log n plus log m space. Okay, so now my space restriction is very, very small. And I can only see each item once. Once I see it, I'm giving you a hint. I have a label and a counter. So I have to update that label, possibly update the counter, and then that's it. I get the next item. I have to, other than what's in the label and the counter, I've forgotten what the item is. Okay? Okay, so how do we do this? So we only have one label and one counter, so there's not too many things we can do, right? So, what, yeah.
Start with the first item that you see, put that in the label, count the number of times that you see it. If you see something else, decrement the counter. When the counter reaches 0, start with the next item that you see.
Yeah, that's it. That's it. So you keep one counter. If you see this, the same thing, you keep one label on one counter. If you see the item that matches the label, you increment the counter. If you see something that does not match the label, you decrement the counter. If your counter's at 0, you can put a next item you see as the new thing in the label. Right? So let me write this down over here. So we'll start with the counter equals 0 and the label equals the empty set, and you say, and you can think of the streaming algorithm as a for loop, for I equals 1 to m, right? If AI equals L, then you're going to do C equals C. Counter plus plus. Okay, else C minus minus. And then if C equals 0, or is less than or equal to 0, then you'll set C equals to 1 and your label equals AI. Okay, so the first time through, you're only going to decrement, but then you fix it with the first item. The counter is 1 and that label is that item. Every time else, you just keep track of this one label, right? So let's go through an example here. Let's say that items are A, B, 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 C, B. Okay, so now B has occurred 4 out of 7 times. So this is a majority. What is this algorithm going to do? So I'm going to have a counter and a label. Okay, so the counter is going to, after each round of the algorithm, the counter will be 1. The label will be A. The counter will be 2, label A. Counter 1, label A. I've decremented because I saw B, it didn't match. I go to 0. The label is going to be B. The counter is going to be 1. Label is still B. Actually, I will, if I'm clever, I can actually, because the counter was 0, I can make this a 1, and then it took this. Is it clear what happened? How I switched this to a 1? I think technically you might not want to, even if you don't do that, the algorithm will still work. But so I've gotten to, I decremented it now with less than or equal to 0. So now I can change it to change the label and the counter to be 1 here. Now we get the counter to 2. The label will still B. It goes back down to 1 because C is something else. Label is still B, and back up to 2. Label is B. So now at the end, I'm going to output B. Right? I should say output L. So I'm going to return L. If it was the majority, I would have gotten it. If it wasn't the majority, then I may have returned something weird, but okay, I went and checked and maybe verified or something. Yeah.
How useful is this if it doesn't always return the majority?
Well, so if there is a majority, it will return it. Is what's going to happen. I'll go through argument in a second. If there's not a majority, it can return anything. Right? So if instead I had said that, let me just throw on top here. I replaced this with an A. Okay, so now nothing is the majority here. Instead, what I'm going to get is going to be the same here. From this point on, I'm going to get a 2A, and then a 1A. This is going to give me a C, or I guess it'll be a 1 and a C, because it went down to 0, and then it'll be a 1 and a B. So it's going to return B. So it's at the end of the stream, so it returns this, even though B is not the majority. Okay, so I don't make any promises if that's the case. So this is basically, if you have to make a promise, then you need a lot more space to solve this argument. So we'll see next how to generalize this and how you can make a stronger promise with a little bit more space. Yeah.
So this doesn't tell you whether or not there was a majority?
No, it's not telling you that. But we'll get to something next that generalizes this and gives a stronger guarantee. But this is just a very simple warm-up. This is a very simple thing. A very small amount of space, you can still solve this specific problem. So think of, if there was a bad event, you always find it. There are no, there are not going to be any, there aren't going to be true negatives, right? You don't want to have someone be a majority and not report it. That's the only thing you want to protect against. Okay, just quickly, let's go through an argument of why this has to work. If you had a, okay, so if you, all we need to show is that if you did have a majority, you found it, right? And so for everything, that means if you have more than half of the items are the same value, let's say B, that means you can essentially pair up every B with the previous or later thing that was not a B. Okay, and so that every B either, and there's going to be at least one left over. So every one that comes after another thing like one of these A's is going to decrement that A and get rid of that counter. Everything, and so that one is used to decrement another counter. Everything that comes afterwards, well, that one was incremented when you saw it, but might get decremented later. But because you have a majority, you have more things than you can pair up. So there must be something left over which will have a positive count. Okay? So this is the argument why this works. There's a little bit more detailed argument in the notes if you want to see it, but hopefully you kind of roughly believe this works. Okay. So this was kind of this was the warm-up. Let's talk about now, we want to do something stronger, and this will be heavy hitters. We want to now, so return okay, so we want to return all Fj such that Fj is greater than some phi times m. And so phi is going to be a threshold now that we get to set. So instead of m over 2, so phi was 1/2, we can set this to be like 1/10 or 1/100. The larger we set it, the more space we'll need. So all of them that are greater than some threshold, but we also wanted to return a stronger, so we don't have these false positives. No Fj such that Fj is going to be less than phi m minus epsilon m. Okay, so we're going to have this error parameter epsilon m, which you can think of being either exactly phi m or something smaller. So if phi is like 0.1, so 10%, epsilon might be 1%. So it turns out the space will actually depend on epsilon. Will enforce that epsilon is going to be less than or equal to phi, and the space we'll need will be something like, the space will be roughly 1 over epsilon, as we'll see. Okay? And then but we still have some region of things that we can't control about. If Fj is in the range phi m minus epsilon m to phi m, then we want to maybe return Fj. Okay, so we're still going to have this space of things where we're going to have some slack. We're not going to be able to do anything about this. Okay, if there's some gap here which we say, okay, maybe I can return it, maybe not, but it's going to be close to our threshold anyways. So you can either set, a bottom threshold at phi m minus epsilon m, or the top threshold, depending on where you want. Okay, so this will be the goal. Now this seems hopefully more reasonable, right? This seems more powerful thing to do. Okay, so what we're going to describe is what's called the Mishra-Rees algorithm. And this is a very simple algorithm that's kind of an extension of this majority algorithm. And in fact, it's going to solve a slightly more general problem, and which is going to be enough to solve this heavy hitters problem. Okay. The slightly more general problem is going to be it's going to return an Fj hat, so an approximate value of the frequency for all j in this is in M, right? For all j in this is in M, in N, such that Fj minus epsilon m is less than Fj hat is less than Fj. Okay? So it's always going to be less than the true frequency, but never too much less. Okay, so if I have all of these approximate frequencies, you should be able to see how I can answer that. If this value is greater than phi m, I always return it. Right? If it's less than phi m, then I don't ever return it. Okay, so I might. Right, so hold on. If it's less than, I got these mixed up. This is a little tricky. So you say for the heavy hitters with phi and epsilon. So if Fj, let's see, if it's greater than, this is Fj hat, is greater than phi m plus epsilon m, if it's greater than phi m, then return. If it's less, if Fj hat is less than phi m, then let's see, so this is always I'll ask you to do something like this on the homework, and this always confuses people, and you seem to be confused now. So if it's, I'm trying to say if it's less than phi m minus epsilon m, to not return it. Yeah, so let's say then, so don't yeah, okay, so let's fix this. Minus epsilon m. Okay, good. Good, all right, so here's what we should do. So if it's greater than phi m minus epsilon m, I should always return it. Because if the true value is greater than phi m, it must be greater, the approximate value must be greater than this, right? Because if I added epsilon m to the true value, then to the approximate value, so if I looked at f hat j plus epsilon m and added that to, let me draw in red here, if I looked at this inequality, I want to say I always return some value if the f hat is greater than fj minus epsilon m. Okay, but if I want the threshold to be at phi m, where I always return it if it's greater than phi m, this was based on this heavy hitters problem, I always return it, then I need to add epsilon m onto both sides. Then this is phi m, and this is phi m plus, this is phi m minus epsilon plus epsilon, right? And I get the right inequality. Okay, so you have to play with these inequalities to kind of figure out where you want to get these thresholds. And we might see another algorithm. I think I took that out this year. There's another algorithm that gets these inequalities differently. Okay, so but this thing is kind of, it's a little tricky to wrap your head around when you return it and when you don't. But you're off by this epsilon m error, and so you set your threshold at phi m with being careful with these epsilon m error parameters, and then you can solve this heavy hitter. Okay. Before I tell you the actual algorithm, or before you are going to tell me the algorithm, there's something else strange here that I claimed I could do. Yeah.
Why restoring the approximate frequency? If we have to allocate space for each item, type of item we've seen, why not just keep the actual frequency?
Good. So this was what I was going to point out. I'm claiming I can return a value for every j, right? This should seem strange. Okay, so I'm not going to do it explicitly. I'm going to do it implicitly. It turns out that for a lot of the values, I can return something that's going to be in this range without storing it. So I'm only going to store a set number of counters and labels, just like before. But for the ones where I have no labels, those are implicitly going to be value 0. Okay, so if the true value is small enough, then I can be between the true value minus this error, and if this range contains 0, I'm allowed to return 0. So I don't actually return it. Essentially, I'm going to have a data structure where you can ask. Right? Or I just tell you all the big ones. The ones I don't tell you implicitly, those are going to be 0. Okay, so that's how I get around this thing, that this holds for all j. So actually, you should think of this as I'll return a data structure where you can ask this question for all j. I'm going to do something, this is a little bit better, in that I'll return to you all the ones which are large enough. Instead of giving you a data structure where you can ask. There'll be something we'll talk about Wednesday, which only gives you the data structure access. So if you want to know which ones are large enough, you have to ask all of them. It turns out you can do bookkeeping, so you don't have to do that, but the bookkeeping will look like this algorithm, it turns out. But you can, so it's important to say you actually, it tells you which ones are large, not you just have the data structure access to it. Does that make sense to understand that distinction? So one is, I can have a data structure, so for every j, I return a value. I can ask and query a value. But if there are lots of possible questions, I don't know where to ask which ones are large. Okay? This is, I'm going to return you a set of values, and all the ones I don't return are implicitly going to be 0. This is a more powerful thing, and we'll see something that on Wednesday that does something weaker than that. Okay. So now let's describe the actual algorithm. How is this going to work? I'll tell you how much space it uses, and then you're going to tell me the algorithm. Okay, so my space for this algorithm is going to be k, better k here, k times log n plus log m. And k is going to be equals to 1 over epsilon. Okay, so let's break this down. When I say I have k times log n plus log m, what is that telling me? What do I have space for?
K labels and K counters.
Right. Good. So these are the labels and these are the counters. So I'm going to maintain a data structure, and which is going to be these two arrays. This is going to be C and this is L, and it goes access into it 1 to up to K, or 0 up to K minus 1, I don't care. Right? So I have this data structure with this access into here. And I'm just going to maintain these counters and labels. Okay, and so initially I will say that counter, let's index them by R, is going to be 0 for all R, and label R is going to be equal to the empty set for all R. Okay? So now how is this algorithm going to run? Again, there's not so much I can do. There'll be one step which will be a little tricky, but let's figure out the basics first, and then we'll figure out this one last step that's tricky. What can I do with K counters and K labels? Yeah?
Well, if you're streaming, right, you can start like filling up your labels and counters, and then you just have to figure out what you're going to do when you get filled up.
Yeah, right, good. So it's going to be just like the majority algorithm, except with more counters and labels. If I see something I have a label for, I increment the corresponding counter. Right? And if I have an empty, if I don't see something but I have an empty label that's not being used, or its counter value is at 0, well then I can create a new label in that place and then start the counter off at 1. Now the question is, what happens when all the counter labels are filled and I see something on my set? Okay, so let's write down the algorithm up to that point, just to make sure everyone's clear on that, and then we'll discuss this last point. So for I equals 1 to m, say if AI is going to be equal to some label R, then we're going to do, let's do it here. CR plus plus. Else, and now I need to be a little bit careful, if there's some CR which is going to be equal to 0, then I'm going to say LR equals to AI and CR equals to 1. Okay? Right, so the first one is if I saw an item that matches a label, I increment the counter. The second one is if for some counter is at 0, then I can take over the label. So if I don't have a matching label and there's a counter which is 0, I'm taking over the label, saying the counter to 1. Now the question is, this else case, what do I do in this else case where I don't have, all my counters are 1 or greater, and I don't have a label that matches? What should I do now? So the good news, it turns out there are two right answers. There's two different algorithms. We'll just talk about one that matches closely the majority algorithm. But what did I do in the majority algorithm? What did I do there?
Threw stuff away.
I what?
Threw stuff away.
I threw stuff away, yeah. So how do I throw stuff away here? I decremented the counter, right?
You just throw out like the bottom half of your.
So I want to throw out, so let's say all my counters are at 7. I have 10 counters, they're all at 7. Or maybe half are at 8, half are at 7.
Just throw all the 7 ones. Half of them.
So I'm going to throw all of them out.
Well, like throw out half of them.
Yeah, so turns out you don't, there's some version of this where, like, you don't want to throw them away because that's too much information. You don't want to throw a count of 7 away. You want to instead, you want to decrease the count down to like 6. I don't want to have one outlier, so I completely throw away everything, right? So instead of throwing them away, I want to just decrement the labels. Turns out I'm going to do this for all of the labels. And this is important. If you do it for half the labels, things will work out okay, with slightly different properties. But for all of the labels, I'm going to decrease them by 1. I'm going to decrement them. Okay, so I'm going to be much harsher. Majority, I just had one label. If I decremented it, maybe not a big deal. Now I'm going to decrease all of the labels. So for R in K, I'm going to do CR minus minus. Okay, so I'm going to decrement these, and then I will return my data structure. Okay, so for all of the items, I'm going to decrease the labels, the counters, for all of them, yeah.
What was fee? What was fee?
Fee, so fee is not in here. I'm solving.
It was on the last page, right?
Yeah, so phi was my heavy hitter threshold, right? But all I'm going to do now is I'm going to maintain all the frequencies up to an error of epsilon, and then I can say, let's say the epsilon is 1%, and I want my cutoff for phi to be 10%. So then I throw away, I only return things that are above 9%.
Should K be 1 over phi instead of 1 over epsilon?
No, it turns out you want 1 over epsilon. You want to make sure you get accuracy on all of your counters. So all of the counters are going to have epsilon m accuracy. And then later, so this is solving this approximate frequency problem. And then if I want to, I can apply this heavy hitters adaptation on top of it. So I'm going to be solving this epsilon approximate heavy hitters problem on the top here. Here. I'm going to solve this problem, this Michel-Gries problem. So for all of my labels J, I'm going to have a counter value which is going to satisfy this property. And so then to solve the heavy hitters with the phi and epsilon, I'm going to filter these. All of the counters that are greater than phi m minus epsilon m, I'm going to return those. Right? So think phi is 10%, epsilon is 1%. Anything above 9% in my counters at the end, I'm going to return those. Right. So yeah. So for the heavy hitters, you need this extra parameter to filter. But often it doesn't take any more space to solve this general problem, so you might as well return this more information. Okay, so, but this is again, is the whole algorithm here. This is the Michel-Gries algorithm. Okay, and so again, the strange thing here is what to do why am I decrementing all of the counters? So for all here, so for all of these values, I'm going to decrement this. Isn't this going to cause too much error? It turns out this is the key to making it work, because I can't do this step I can't do this step too many times, okay? So this step, every time I do this, I have all my counters must be full, and I'm decreasing k of them. So I can do this step at most m over k times. Because I know the sum of all my counters has to be at most m. At most m, that's the number of items in the string. And every time I do it, I've decremented one from every counter, and the value is still non-negative, because they were all greater than 0. Okay, so it happens at most m over k times. And so if I set k equals to 1 over epsilon, then this is equal to epsilon m. Okay? This is from setting k equals 1 over epsilon makes this epsilon m, meaning that for any of the counters I'm keeping track of, I've decreased it at most epsilon m times. So my error is at most this much. It's never an overcount, right? I guarantee that my approximate counters are never too large, which is true. I only increment them if I see something that matches the label. And it's never too small, because I decrement them at most this many times. So the fact that I'm decreasing all of the counters allows me to bound the error. It's pretty cool. Yeah?
What if you decrement and you have several counters at 1 and they all go down to 0? Do you return those counters with a value of 0?
Yeah, so then I can return those, but I know the labels I can keep the same, but the counters I return are 0, so you can do with them as you like. You know they aren't very meaningful. Yeah, so you can still return them, and then you use this phi value to filter them. Right, so yeah, so this is a really cool algorithm. It turns out that if you need this much space in order to solve it. If you want to solve this approximation guarantee I had on the previous page, you need to have this much space. You need to have this many labels. You can't do any better, at least in a string, right? But it could be that if they, and the way to think about it, I can have at most k items with this large of a count. I can't have more than that anyways. Right? If I want to return items that occur more than 10% of the time, there are at most 10 such items. And that's how much space I'm using, right? So roughly, or up to that much error, right? So the error depends on the size of the number of items that you can have that have have the counter of the amount of error that you have. So the proof you need this much space requires this, information theory arguments that we're not going to get into. But you can't do any better than this space for this problem if you're doing this in the string. It's a very simple, cute algorithm. It turns out most algorithms in the streaming setting are going to be extremely simple, but kind of figuring out what they are and how to analyze them can be complicated. This one is also fairly simple to analyze. There's some more details I didn't go over, but hopefully you roughly buy this argument that I've decremented at most m over k times, and that means the error is at most epsilon. Yeah.
I have a question.
Yeah.
Do we know the number of fj that satisfy the constraint? I mean, can we make sure that there is at least k fj is greater than the fj minus epsilon? No.
Good. So let me repeat the question. So, can there be more than k equals 1 over epsilon j in n
Actually, I want to.
such that fj, how about I answer this question?
I want to ask about less.
What?
How about less?
So greater than epsilon. Okay, can there be fewer than that? Yeah, so if there are fewer, then my counter will be smaller, and I can filter it later however I want to.
But maybe we will have some number we don't want, like something just appear at the end.
Yeah.
And we up that.
Yeah, so it's possible I will output a label that does not have a very big counter, right? And so then I can do with that like what I want, right? So let's say my total error on the count of these things is going to be it's like 1%, right? So I'm going to keep 100 counters and labels, and so that means I have 1% error on all of those frequencies. So let's say I return a frequency and I know the total number of things that only occurs is the last 0.5% of the data has this. And so I return a counter and a label that has 0.5%, right? So I know that, okay, it has at least 0.5%. The true count is larger than it. So if I go back up to my guarantee, so this is my, right, so remember, this is my guarantee here. For everything I return, it's going to be between the true value and the true value minus epsilon m. So think this is like 1%. Right, so if something comes at the end and so it shows up because one of my counters got down to 0 and I filled it in with something that came at the end, but it didn't occur that often, then the associated counter with it is going to return something that has to be small. It's going to be smaller than the true value, right? So if the true value was only like 0.7% of the time, right? So if there was f of j, the true value, so this is the true one, if this is equal to 0.7%, then I know then it means that f of j hat must be less than or equal to 0.7%. I'm not going to overestimate anything. So if I want to filter at 1% or at 5%, even if I return this value, let's say so maybe this will be equal to 0.5% of the data. So if I see this value, I know I don't need to worry about it. I know this is in the noise. I know what my epsilon m parameter is as part of the input to the algorithm. So I know if it's less than that, this is in the noise part of the data, and I can just kind of drop it. Okay, great. Yeah, but, okay, so this is another interesting question. Let's just come back and make sure we answer this. I only have k1 over epsilon counters, and so can I have more than j values that have a count greater than epsilon m? Then I wouldn't be able to do this, right? Is this a problem? Yeah? I think this is the problem. Okay, so let's say I have k equals to 10. That means that epsilon m is going to be equal to m over 10, and this is roughly is 10%. Okay, so now if I have 11 things, 11 items, so that are this is j, and this is the percent of the data. So if this one's at 11%, this one's at, they're all at 11%. So this is j equals 1 up to j equals 11. Right, so they're all at least 10%, or let's say it's exactly 10%. Then the total percent is going to be 11 times 10%, which equals 110%. Right, so unless you're playing in the NFL, this is not possible. You can't give 110% of something. So we're okay. We can't possibly have more items than we have space for, than we have space guarantees for. Yep.
I don't know if I missed this. Is there like a good way to choose your fee?
So the fee is a modeling choice. So it's up to you what you want to filter out. Fee tells you what, you care about things that occur that more than a certain percentage of the time. And you should talk to people in networking or whatever who model these sorts of, say, denial of service attacks, whatever you're trying to finance this of. So I mean, if you're just using this to say approximate some probability distribution, I would probably do something like setting fee equals to 2 epsilon, right? So then you're so then you're throwing anything. You can say it's probably noise if it's less than half of the if what I return is less than half of my threshold. But you might as well actually keep everything because you have no overcounts. So it doesn't really harm you to hold on to this other stuff. The heavy hitter problem was something that the people in the database community said, this is an interesting, important problem we need to solve. And then these streaming algorithms solved it by using this more general technique. And they had come up with fee parameters that mattered for various problems, but it's problem specific. Good, okay, so I have about 10 or 12 minutes left, and I wanted to show you another cool algorithm. So we're just going to do this briefly. And so this is for this, let me just review this old picture I have for this, where do we go here? For this quantiles problem, okay? So let's look now at this quantiles problem. Right, so now I have things coming and they have an ordering to them. Think of these are times people spent on the website. They are not coming in the time order. They could be, instead it could be money instead of time, some continuous variable. Okay? And now I want to approximate things in the ordering. Okay? Again, if I want to have, so that I get this error, this epsilon error in the height, right? This value everywhere is between 0 and 1, so epsilon tells me a probability I'm off by. So if epsilon is 0.01, then I'm off by, a probability of 0.01. Okay? And so there's a way to do this offline with size exactly 1 over epsilon to get this everywhere. And the idea is that you take all of your data and you sort it and you take evenly spaced points, right? So I'll take every, so if my error is 1/3, then what I'm going to do is I'm going to take evenly spaced points in this sorted order, well, just the orange ones I've circled, and then this is going to be an approximation. I can just return these points. So in a stream, this is much harder to do. In a stream, it turns out that in a stream, you're going to need the number of items you keep track about is going to be 1 over epsilon times log 1 over epsilon. And just this last year, someone figured out how to do this. There are practical algorithms that are a little bit larger than the log factor. But, so in a stream, you need a little bit more space because you're going to get some error. If you accidentally throw away a point, it turns out maybe that was the point I needed. But these algorithms are a little bit complicated, and I definitely can't solve them in 10 minutes. Okay, so instead I'm going to tell you a different problem that's related, and I'm going to show how to solve that problem in 10 minutes. And this is going to be kind of like this majority thing. It's going to keep a single counter and a single, actually just a single value in my time domain. Okay? And the goal is I'm going to try and find, so let's redraw this picture. So here we go. So we'll call this called a frugal algorithm because it takes it's only using one counter. So frugal algorithm for the median. Right? So if I have this picture of the cumulative density function going from 0 to 1, then the point where it hits 0.5, this is, whatever data point is right here is the median of the data points. That means that of my data, I'm going to have half of it, so half of it's going to be on this side, and half of it's going to be on this side. Okay? So this median tells me something about these quantiles. Now, if I know the median, that's kind of like the 0.5 quantile. So the 0.5 quantile is equal to the median. And if I could keep a lot of these instead of the 0.5 quantile, I could keep the 0.1 quantile, the 0.2 quantile, and so forth, then that's going to actually tell me a lot about this cumulative density function. Right? And basically, I've got this value here, but if I also had it at all these, if I also had it at all of these other values, and so forth, if I had all of these values here, then I'd know it accurately enough the whole distribution. In fact, if the gap between these was epsilon, this was going to be sufficient. Okay. So, but I'm just going to solve the problem just for the median, and then I'll mention on time how to generalize it to other values as well. And so for the median, I'm only going to, again, need one counter here. This is a very kind of cool, cute algorithm. Okay, so I'm just going to keep one counter, and that's it. So I'm just going to keep a counter L. Okay, and let's just say it's in a discrete domain. It could be a large domain, it can be a discrete one, and so I'm going to, and initially, let's say the counter is 0, but it might be better to start someplace else if you do something. But so I'll start with the counter at 0, or this. Sorry, this should be a label. So label 0, it's in the domain n, so this is log n space. Okay, and so now I want to approximate the median with this. So how would I do that? With only one counter, that's all I have. I have a counter that's 0. So I'm going to write an algorithm for I equals 1 to m. Okay, and then I'm going to have a simple if condition. If AI is greater than L, then I'm going to do L plus plus. Else, if AI is less than or equal to L, or it's less than L, L minus minus. And then I will return L. Okay, so this is again like super simple. If I see something greater than my current estimate, I increment the counter. If it's less than the current estimate, I decrement the counter. Okay, so if I'm at the true median, then of the things I see, half of them should be greater, half of them should be less. Right, so it should move up and down a little bit, but basically should probably stay the same. And so the error bounds on this algorithm are not as strict as the other ones. This is a more challenging problem. You can say something like, so the error analysis of this one is going to be something like that my, let's call, I'm going to say that the L, my estimate I'm returning is going to be, need to define this. So I need to define the rank of so I'm going to get an estimate of the fraction of data that's less than, so rank is the number of items which are less than or equal to L. Let me write this down. is the set of AI in A such that AI is less than or equal to L. Right, so this is, instead of the frequency, this is the count of the things which are smaller or equal than L. And so rank of L over M is going to be my approximation of the height on the y-axis here. Right, so this is going to give me, so I'm going to guess some value. So this is the true median, and I'm going to guess L, and then the rank is going to be over here. So this is going to be the rank of L over M. Is going to be this value, and I want that to be close to 0.5. And I'm going to say that this is in 1/2 minus epsilon, 1/2 plus epsilon, as long as, so with probability, and this is assuming something on the distribution, 1 minus delta for M. So this is going to be the true median times log 1 over delta divided by epsilon. Okay, so I'm going to get, I'm going to get some other error bounds that, so after this many steps. Okay, so as I take more and more steps, I'm going to get more and more accurate representation in this algorithm. And so because I started at 0, it's going to take at least the median number of steps for me to get there. So if I start out at something with L equals something larger, then this value is going to be smaller. So if N is very large, this isn't going to be as useful because it's going to take a large number of steps to get there. And so the more steps I get, the accuracy is going to come down. And then there's going to be some analyze like a random walk around the true value rule. I think that's where these bounds come from. So one of the issues is that I increment exactly by 1 or decrement by 1. There's a version of this where you can keep an extra counter that tells you at the beginning take bigger steps, and as you get closer, take smaller steps. So there's a version that takes 2 counters that does that. But this with 1 counter is already getting it's already getting some sort of guarantees. And then there's a version, so let's say instead that I didn't want to get the 0.5 approximation, instead I wanted to get, say, 0.75, then what I'd say is that if so if I want a value, say phi equals 0.75, and I want to estimate this value instead, then I do this step. If I get here, then I say with probability 0.25, which is 1 minus phi, and I do this with probability 0.75. So I take this increment or decrement step proportional to how far away this is. So if I'm trying to have something that is large, I think I have these backwards, but if I have something that's large, I expect to see something smaller than it. So I don't always increment. So if I want to find a smaller quantile, I expect to see something larger than it. So if I see something larger, I don't always increment. And you can play with this, and you can get similar bounds for these sorts of quantiles. Again, it's just a very simple, cute algorithm. Yeah.
So do you choose what probability you want based off what you think the distribution in your data is? Because like if you have like 2 Gaussian curves and a huge gap around the median.
So this is trying to learn the distribution. So what I'm doing is this phi that I mentioned here at the end, this is trying to tell me which quantile I'm trying to estimate. So I can run a different one of these estimators for each quantile. If you want to estimate all the quantiles, this is not quite the right way to do it. If you just care about a couple of them, because you want to filter, say, do some confidence intervals or something, then you can just maintain a couple of these this very simple Qt algorithm. If you want to maintain all of them, you need a little bit more space. You need a bunch more counters, and the algorithms are more complicated to update. So this is it for today. On Wednesday, we'll talk about some completely different ways. We'll talk about these sketching approaches towards the same heavy hitter problem, and also talk about some other ways of calculating these frequent things. So we'll use these randomized hashing approaches to solve some of the things, and there'll be different modeling and computational trade-offs that we'll get to see.